Hello, welcome back to part 2 of chapter 14. We're talking about correlation and regression. So now we're going to 14.3, which is correlation. So our correlation coefficient r quantifies a linear relationship with a number between -1 and 1 when all points fall on a line with an upward slope of r equaling 1. 1 is like a perfect correlation. When all data points fall on a line with a downward slope, r is -1. So a negative association. When data points trend upward, r is positive. When data points trend downward, r is negative. The closer r is to 1 or -1, the stronger the correlation. So here are a couple of illustrated examples. This would be a perfect positive correlation of r equaling 1, and a perfect negative correlation of r equals -1. A strong positive correlation would be 0.9, a moderate positive correlation of 0.05, strong negative correlation of -9, and a moderate negative correlation of r equaling -0.5. So how do we calculate r? So r is equal to 1 over n times the sum of zx and zy, where zx equals our xi minus x bar over sx, and zy equals yi minus y bar over sy. The correlation coefficient tracks the degree to which x and y go together. So remember, this is remember we call z-score quantifies the amount a value lies above or below its mean in standard deviation units. When z-scores for x and y track in the same direction, their products are positive, and r is positive, and vice versa. If they go negative, then there's a negative. So let's go back to our illustrative example of the countries and their cigarette consumption and the lung cancer. So here we have our x and our y columns here. Before I get there, notice at the top we're going to find our x bar. So we're going to take the total amount of x, our sum, divided by the total number of countries, 11, and so we have our x bar for the total, and y, same thing, add up all our y values and divide by 11. So here's our x bar and our y bar. Our standard deviation for x and our standard deviation for y noted here. And now we figure out our zx value, which when we take the xi value, so you would take like your 1300 minus your x bar value divided by the standard deviation, and that's what this column is telling us here. Is our z of x value and the total at the bottom, and our z of y value with the total at the bottom, and our z times y value over here. So when we plug all the information we need into our equation up at top, 1 over n minus 1 times the sum of zx times zy, we got 1 over 11 minus 1 times 7.374 right here equals 0.737, and that is our r value. So our r would be 0.737, which we would say is a pretty strong correlation. It definitely it's higher than 0.5, so it's over moderate, but it's not perfect. So I would say it's a strong correlation as well. So going back to calculating r, so in practice, we have computers and softwares that will do this for us. If you have a scientific calculator, sometimes there are ways you can input data and get your r value and also graph them. There's also plenty of tools that you can use online. I'm not against using them, but for the purpose of the class, we will be calculating it by hand. Of course, all the information that we were trying to gather in this data set, we can calculate by getting standard deviations, figuring out the averages, and plugging them all in there. It would definitely take some time, but is doable. If we were to put our data into SPSS, this is what it would pop out looking like. And as you can see here, there are Pearson's correlation 0.737. That is our r value there. So interpretation of the r value, direction, remember the sign of r indicates the direction of the association, whether positive or negative or no association. close to r is to 1 or -1, the stronger the association. So when we want to figure out the coefficient of determination is the square of the correlation coefficient, r squared. That's what it's called. This just quantifies the proportion of the variance in y, mathematically explained by x. So for the illustrated data, we had an r value of 0.737, and if we were to square that, so you get r squared equal 0.54. Therefore, 54% of the variance in y is explained by x. That's how we determine the coefficient of determination. We did that. So continuing on, reversible relationship with correlation. It does not matter whether variable x or y is specified as the explanatory variable. Calculations come out the same either way. This will not be true for regression though. Outliers can have a profound effect on r. This figure has an r of 0.82 that is fully accounted for by a single outlier. So as you can see, this is your data points go in a straight line up here except for one outlier found over here, and we have an r value of 0.82, which is a relatively strong r value, and it's all because of just one outlier. So outliers can have a profound effect on r. Here's linear relationships only. Correlation applies to linear relationship. This figure shows a strong nonlinear relationship. So as you see, it makes this arc, and we have an r value of 0 because it's a linear relationship. Correlation does not necessarily mean causation. We want to be aware of lurking variables. A near-perfect negative correlation, r equals -0.98, was seen between cholera, mortality, and elevation above sea level during a 19th century epidemic. We now know that cholera is transmitted by water, so the observed relationship between cholera and elevation was confounded by lurking variables, which was the proximity to polluted water. Here's your negative correlation that was found with cholera mortality and elevation above sea level. But we all know that that this is not true, so just beware. I don't know why that says 5, should say equal. Alright, hypothesis test. Let me go back. So, hypothesis test. So, a random selection from a random scatter can result in an apparent correlation. We conduct the hypothesis test to guard against identifying too many random correlations. So, once again, when we state a hypothesis test, we're going to have rho here as our hypothesis testing. And we're going to have our null hypothesis state a difference of nothing. So we'll have rho equals 0 versus alternative hypothesis of rho not equaling 0, which is two-sided. And or you can have a right-sided or left-sided hypothesis test based on the greater than or less than symbol. So our test statistic is going to be our t-stat is going to equal r over the standard error of r, where the standard error of r is 1 minus r squared divided by n minus 2, take the square root of that value. And then degrees of freedom is going to be equal to n minus 2. Once we have our t-stat, we're going to convert the t-stat to a p-value with software table C. Remember, table C is just going to give us the critical value, which we determine what the critical value is based on the data set in front of us. And if we have a t-stat above that value, we find significance. If it's at that value or less, we are not going to find significance. So for our illustrated example here, we have rho equals 0 versus alternative hypothesis rho is not equal to 0, two-sided. Our t-stat, so standard error of r, 1 minus 0.737 squared minus 11 minus 2 equals 0.2253. We have our t-stat of 0.737 divided by 2253, 0.2253 equals 3.27. With the degrees of freedom equaling 9, which is 11 minus 2. So when we look at our critical value in the software and convert it to a p-value, we get a p-value equaling 0.0097, which is the evidence against the null hypothesis highly significant. Is less than 0.01, but not less than 0.005. So less than 0.01, we'd still say it's highly significant, is what we tested for. Here we're going to have confidence intervals for rho, which I stated in the beginning, but you don't need to know. Just know that these are the equations to calculate the confidence interval for a lower confidence level and upper confidence level. We have our R minus our all intents and purposes call this our W hat over 1 minus R times W hat. Same in the bottom, but for upper we're going to use addition signs, where our W hat's going to equal the square root of our t degrees of freedom of 1 minus alpha squared divided by our t degrees of freedom 1 minus alpha plus degrees of freedom. Note to square again, and degrees of freedom is equal to n minus 2. Once again, I'm just going to go over that. Here's an illustrated example if you like to look over. There's more reading in the book you can go to. What we do want to go over is the conditions for inference. So remember, they have to be independent observations. Bivariate normality. R can still be used descriptively when data are not bivariate normal. Bivariate normal meaning we have kind of a bubble going into a third axis point, or z-axis, so 3D in a sense. And that's where I will stop this video talking about correlation. So remember, we don't have to know the confidence interval other than knowing it for theoretical purposes and knowing the conditions for inference, but we do want to know how we can set up a hypothesis test and how we do our test statistic from there, and then how we calculate an R value using this equation here and finding our standard deviations and our averages for each point, and then tracking to see if there's a positive or negative R value for the association with it. The next video we will go over will be 14.4. We'll be talking about regression. I'll see you there.